hits the ground over here. Before we just draw the ground color to the pixel, let's first check if that point is in shadow. To do this, we cast a ray from that point towards the light source. If it is blocked by an object, as it is here by the sphere, that tells us that we are indeed in shadow. Of course, in reality, the rays come from the light source, not the camera, but most of them will fly off in other directions and miss the camera, so by doing it in reverse, we get to save time because we can just calculate the few rays that do actually hit the camera. Here's my little scene again, this time with shadows. I also made the spheres bob up and down, just for the joy of it. The last thing I wanted was reflections, so now when a ray hits something, it should bounce off and keep bouncing until it reaches the max bounce limit that I defined. So the color for this ray should be a combination of this sphere's color, and the sky color. Okay, now I'll add some simple shading in to make this look a little better, and then I'm just going to scooch the camera over a little so you can see this better, and increase the light bounce limit to 1, and all of a sudden you can now see reflections. If I increase the bounce limit to 2, we can now see reflections in those reflections. At 3, reflections in the reflections of the reflections, and so on. Now, the article I followed does go a lot further than this, so I think it's really worth checking out if you're interested. I'll leave a link in the description. But by this point, I was feeling ready to tackle the task of converting my erosion code to a compute shader. Well, it was a bit of a bumpy ride, but once I'd finally verified that it was working, it was time to put its speed to the test. So I set up a 1500 square map with 600,000 simulation iterations, which the old erosion code can crunch in about 43 seconds. Anxious to see if my work would pay off, I pressed run, and just 1.5 seconds later, the erosion was complete. So that means that it's now feasible to experiment with larger maps like this one, which of course I'm very happy about. I also inverted the height map generation to a compute shader, and got a similarly dramatic increase in speed. Anyway, this video is titled Compute Shaders, so I should probably spare a moment to actually talk about the things. In the old code, I had this loop to sequentially simulate each droplet, but in a compute shader, there's this function here which is called the kernel. I have the code to simulate a single droplet in there, and the shader then runs many of these in parallel. The num_threads attribute lets me specify how many threads should be executed in a group, and when the shader is dispatched from the main thread, I can specify how many total groups I need. So if I want to simulate 100,000 droplets, I could have a group size of 1 and ask for 100,000 groups, or I could have a group size of 1,000 and ask for 100 groups. If I'm honest, I really don't know a thing about GPUs, so I don't know what this actually means, but I have found through trial and error that, in my case, setting the group size to the maximum of 1024 gave me the best results. To pass the original map data to the shader, and then get back afterwards, I need to create a read-write buffer of floats in the shader. In the C# script, the syntax for setting the data looks like so, and for getting it back, like so. If you're interested in learning more about this topic, I'll link to all the resources I used in the description. But for now, that is everything for this coding adventure, so until next time, chill. Hi everyone, I've recently been messing about with creating little procedural planets, and there's still loads of things that need to be improved, but by far the most upsetting thing is how the sky is pitch black even in the middle of the day. So to fix that, in this video I'm going to be attempting to create some atmosphere. My first step is going to be to write a post-processing shader that will be responsible for drawing the atmosphere around our little planets. So this here is the fragment program of that shader, which will be run for every pixel on the screen. So for example, if I get the current pixel color and return 1 minus that, we'll end up with this. That's not terribly helpful though. Instead, I want to draw essentially a bubble, so we'll need to figure out where the view from the camera intersects with a sphere around the planet. Happily, I already have this bit of code from the simple ocean shader last video, and that'll tell us how far the view ray has to travel to reach the surface of the sphere, and also how far it travels through the sphere. To complicate matters a bit, if we're looking at the planet, then the distance through the sphere should be cut short by the planet's surface. So let's dive back into the shader, and I'll start by getting the origin and direction of the view ray for the current pixel, which we can then give to that ray sphere function to find the distance to and through the atmosphere. I have long since lost any faith in the code I write, so to quickly check that this is doing what I hope it's doing, I'll return the distance through the sphere divided by the sphere's diameter, and actually, that does look about right. We still need to account for the planet's surface though, so we can sample from the camera's depth texture, which will just tell us how far away whatever was drawn to this pixel is. We can then correct the distance through the atmosphere, like so. This is the result now, but annoyingly you might notice that the ocean isn't being accounted for, which is because it's actually a post-processing effect as well, and not included in that depth texture. So I'll need to quickly go back yet again and just calculate the distance to the ocean sphere over here, and then the distance to the planet's surface is whichever is smallest between the scene depth value and the distance to the ocean. Just to liven things up a bit, I'll multiply the output by the view ray's direction, with x, y, and z being interpreted as red, green, and blue, and that'll give us this groovy result. So, we've got our little bubble, but to make this actually look like an atmosphere is clearly going to take some work. I do have some idea how to approach it though, because a little while back I experimented with clouds, and the basic idea there was to represent the density of water droplets by mixing layers of noise, and then approximate how light might be scattered as it travels through that space. The scattering of light is also what makes the atmosphere visible, so I'll be able to draw on what I learned from these great resources during my research for the clouds. But I am also going to be using accurate atmospheric scattering by Sean O'Neill as my guide for this project, because it looks like a really nice breakdown of how to actually compute these intimidating looking scattering equations. So an atmosphere is made up of loads of tiny little molecules like nitrogen and oxygen in the case of Earth, and these will be quite tightly packed together close to the surface, but as we go higher and higher, gravity gets weaker and there's less gas pushing down from above, and so the little molecules will be spaced further and further apart, and at a certain altitude, for practical purposes, we'll say that's the end of the atmosphere. Now, light from the sun enters the atmosphere, and its interactions with the gas molecules cause it to scatter about. The type of scattering we have here is called Rayleigh scattering, which happens when the size of whatever's doing the scattering, like our gas molecules, is a lot smaller than the wavelength of the light. In this case, when the light interacts with the molecule, it will mostly be scattered forwards and backwards, and less so in a perpendicular direction, giving us this pleasant peanut pattern. Happily, unless you despise blue skies and sunsets, the amount of scattering is dependent on the wavelength of the light, with violet light, for instance, being scattered about 10 times as much as red light. Intuitively, I guess this makes sense if you think how shorter wavelengths will have more opportunities to interact with stuff, but I'm not sure if that's how it actually works in the confusing quantum-y realm of light. Anyway, this is in contrast to Mie scattering, which occurs with things that are roughly the same size or larger than the wavelength of light, such as dust particles or water droplets in clouds. In this case, the light is predominantly scattered forwards, and all wavelengths are affected pretty much equally, which is why clouds appear greyish-white, for example. Again, I guess it makes sense that when the things you're interacting with are big, having a shorter wavelength doesn't really help you meet more of them. For today, though, I'm just going to focus on Rayleigh scattering. So, as we saw, violet light scatters the most, so it'll be coming from pretty much every direction, meaning wherever you look, it's going to be entering your eyes, making the sky that distinctive violet color we all know and love. Okay, after a little research, apparently the sun doesn't produce that much violet light, and our eyes are also less sensitive to it, so blue predominates. Green light doesn't scatter as much as blue does, and red light even less so you won't see much of them unless you're looking directly at the sun. However, if our view is all the way an extra long journey through the atmosphere, so almost all of the blue light is going to get scattered away before reaching the viewer. Most of the green light will be scattered away too, leaving primarily the red light, which will scatter a bit as well, giving us a beautiful fiery sunrise or sunset. Unfortunately, if we were to try simulate all these little interactions, it would take hours and hours to render a single frame, which wouldn't make for the most exhilarating gaming experience. So we're going to need to resort to some crude statistical approximations. Let's get back to the code editor, and I'm going to make a little function called calculate light, which will take in an origin, direction, and length to describe the view ray of the camera through the atmosphere for the current pixel. The only way for that pixel to be illuminated, at least in our simplified model, is if light travels from the sun and gets scattered into the path of the view ray, which I'll refer to as in-scattering. Now, this could happen anywhere along the view ray, but in order to calculate it, we'll need to pick a finite number of points, with more obviously being better for quality, but worse for speed. So in the code, I'll set the first in-scatter point to be the ray origin, and then I'll run a loop for the number of points we want, and move the point along the view ray by the step size, which is just the distance between the points, and we can calculate that like so. I'll then also make a variable to keep track of the total amount of light scattered in across all these points. So now the question is, how much light from the sun is actually reaching each of these in-scatter points? Because some of it is going to scatter away before it gets there, and the amount that scatters away depends on the average density of the atmosphere along this ray where the light is traveling, or as it seems to be called in fancy physics terms, the optical depth. So in the code, let's first figure out the length of the sun ray, which we can do using Rayleigh sphere function from earlier. Then to calculate the optical